After that short little unit on an introduction into functions with domain and range and function notation, this unit focuses specifically on linear functions, functions whose graphs are lines. So today we're going to focus on a very important piece of linear functions, and that is slope. So that's what we're going to focus on today. And slope is nothing more than a rate of change. And here's a definition from our textbook on rate of change. Rate of change shows the relationship between two changing quantities when one quantity depends on the other. So then the rate of change is the change in the dependent variable over the change in the independent variable. So we're going to look at an example where there's a dependent and an independent variable. This table shows the distance that a marching band marches over time. So after 1 second, they've marched 260 feet. After 2 seconds, 520 feet. After 3 seconds, 780 feet. And after 4 seconds, 1,040 feet for the total. Now, to determine which one is the dependent variable, ask yourself what depends upon the other, or what makes more sense. Does it make more sense that time depends upon the distance that they've marched? Or does it make more sense that the distance that they've marched depends upon the amount of time that they've marched? Well, I would say that the distance, let me change over to pen here, that the distance, sorry Kaylee about the clicking on the screen, I'm trying to land softly on the screen, and anyone else that may be bothered by that, I'll try to land more softly on the screen. But anyway, the distance depends upon time. So what that means is then that the distance is the dependent variable. So that's what we're going to subtract on top. So between each pair of consecutive points, so we're going to go from 1 to 2 seconds first. So to calculate that rate of change between 1 to 2 seconds, we're going to take the change in the distance, which is 520 minus, I'll do that below. So from 1 to 2 seconds, we take that 520 minus 260 over 2 minus 1. Okay, because the change in distance is 520 minus 260, and the change in time is 2 minus 1. So we end up with 260 over 1, or 260, and the rate of change is feet per second. Okay, so from 1 second to 2 seconds, they are basically marching 260 feet per minute. Wow. Okay, 260 feet per second. They'd be flying. It's tough to march that fast. I know, I was in the marching band in high school, and I would not have been able to march at 260 feet per second. 260 feet per minute, still kind of cruising, but I think you can do that. So anyway, so from 2 to 3 seconds, to find the rate of change from 2 to 3 seconds, we're going to take the distance at 3 seconds, which is 780, minus the distance at 2 seconds, which is 520. And we're going to divide that by the change in time, 3 minus 2. So again, we end up with 260 on top, 1 in the bottom. So between 2 and 3 seconds, again, they're marching at a rate of 260 feet per minute. Have I been saying seconds again? Holy cow. But that would be cruising. I would challenge any of you to march at 260 feet per second. I don't think you can do it. So then from 3 to 4 seconds, we take the distance at 4 seconds, which is 1,040, and subtract the distance at 3 seconds, 780. That would be the change in the distance over change in the time, 4 minutes minus 3 minutes. I'm stuck on seconds for some reason. That's okay. So then, between 3 and 4 seconds, again, they're averaging 260 feet per minute. Much more doable. So what this tells me is, well, the rate of change is constant no matter which pair of consecutive points you find or you use. Then the rate of change between 1 and 3 seconds. So we're going to go from 1 to 3. And from 1 to 3 seconds, we're going to take the distance at 3 minutes. 3 minutes, which is 780. And we're going to subtract the distance at 1 minute, which is 260 feet. And we're going to subtract the time, the 3 minus the 1. So when we do that, we have 780 minus 260. That is 520. And when we subtract the time, 3 minus 1, that's 2. So 520 divided by 2 is 260 feet per minute. And then from 2 to 4 seconds, we're going to take 2 to 4 minutes. My goodness, 2 to 4 minutes. 2 to 4 minutes. We're going to take the distance at 4 minutes, which is 1,040, and subtract the distance at 2 minutes, 520. And on the bottom, we're going to subtract the time, 4 minus 2. So, subtracting those distances, we have 520. That's 1,040 minus 520. 4 minus 2 is 2. And again, we're at 260 feet per minute. And then finally, from 1 to 4 seconds, we're minute. Oh my goodness. This is ridiculous. We need to change this to minutes. That's why I keep saying it. Minutes. Minutes. Everyone change that on your worksheets right now. Don't let that float around the building. My goodness, minutes. So from 1 to 4 minutes, we are going to then find the rate of change from 1 to 4 minutes. So we're going to take the distance at 4 minutes, which is 1,040. Subtract the distance at 1 minute, 260. And then on the bottom, we subtract the times. So 1,040 minus 260, that would be 780 over 3. So again, when we take 780 divided by 3, we still have 260 feet per minute. Now, one thing you might notice is that we got 260 feet per minute no matter which points we dealt with, whether we dealt with consecutive points, whether we jumped from 1 minute to 3 minutes or 2 minutes to 4 minutes, or whether we took the entire amount of time from 1 minute to 4 minutes. Either way, we got 260 feet per minute. And since that rate of change was constant, that tells me that this is a linear relationship, as that rate of change is constant. Okay? In the next video, we're going to talk about how we find the slopes of different lines, whether it be graphs or given the slope between 2 points.